Oh, let me put mine. Okay. All right. So we're working on these problems here. Is everyone able to record that wants to?
Sir, could I get permission to record?
Okay. Who am I speaking to? Who is just speaking? Who is speaking?
It's me, Philip, sir.
Me. I know. Okay. Okay. Gotcha. Okay.
Thank you.
He doesn't help me, Philip. I recognize some voices. Okay. All right. So let's make sure we know how to do these. Like I said, the last one's a little tricky.
And the final
Okay.
and the MATLAB assignment.
Okay, but what about the final?
My question about the final is it going to be taken in a similar format as we have taken previous exams?
Yes, I'm not going to change it.
Okay, so we'll still have like a 2-day thing for the final.
Exactly the same. I'm not going to change that. That wouldn't be right to change it.
Okay, thank you very much.
Okay, so it's a little dark. Why is it so dark? I see something. Is that better? Okay. I'm going to give you a couple more minutes. I'm actually not doing anything new. And on Monday, we'll learn how to solve a system of differential equations and practice it on Tuesday. And then we'll have the exam 4 on Tuesday. By the way, I updated the Laplace transform lecture notes where I have a section that has more example problems. Let's see. As a t, let's see, this is going to be, when I square this, I'm going to get e to the t squared plus t. Now I'm going to get the middle term. That's going to be e to the t to the 4th, right? Plus t e to the 6th. Right. Hopefully everybody got that far. Okay, so now what is t, right? Let's see. I added it to my notes that oh no, okay, that's for the inverse. Okay, so t is just going to be 1 over s, right? Right. If I just had t, it's 1 over s, but I got t times this exponential. So this first term here, the Laplace transform of t e to the 2t, right? That's just going to be equal to 1 over s minus 2 squared, right? We're using the S transactional theorem shift. Okay, so this whole thing then is just going to be 1 over s minus 2 squared plus, do I have a plus sign there? Yeah, plus 1 over s minus 4 squared, right? Plus 1 over s minus 6 squared. Okay, so that's our answer. That's the Laplace transform for this. Okay, not too hard. The next one, let's see. The next one, remember now let's see, the Laplace transform for sine. Let's just look at sine, right? The Laplace transform of sine is s plus k squared. I want the Laplace transform, not the inverse. So Laplace transform of sine of kt, right, is equal to k over s squared plus k squared, right? That's the Laplace transform of the sine of kt, all right? But I got this t here, right? I got the t here, so I'm multiplying this by t. So we have to use the theorem that so now the Laplace transform of e to the t sine of 3t, this is going to be equal to k s minus 1 squared plus k squared. Okay, because remember what we're doing, but we're using this, we're using the fact that the Laplace transform of e to the at, of e to the at, that this is equal to, right? Whatever this function is here, I have to shift it a. So see, this is so I have to shift this 1 here. Okay, so that's the Laplace transform of the second problem. Okay, so the third problem. Someone have a
Professor?
question? Yeah.
Yeah, I had a question about the first one.
Okay.
When you expanded it, wouldn't the middle term be 2t?
Yeah, this is 2t, right?
No, the middle term.
No, the
2t e to the 4t.
The middle term. Let's see, the middle term. This is going to be this times this. Oh yeah, you're right. There's a 2t here. You're right.
Yeah, that's what I was asking.
Yeah, you're right. There's a 2t there. So let's see. So yeah, and then there's a t here, a 2 here. Good. 1 point off for me.
All righty, thank you.
Oh, thank you. Okay. Right. Skip that too. Yeah. See, is it right in my notes? Yes,
Excuse me, Professor.
yes.
Sorry. Did you only opt to write why did you write K instead of putting in 9 for the second problem?
Yeah. The k would be right, but we want to put this in as 9. We want to put this in as 3.
Okay.
Okay. All right. Other questions, other mistakes. All right. So all right, so there we are. All right, now problem number 3. Let's see, I'll do it this way. Problem number 3, so we could let's see. Problem number 3. Okay, so what I'll do in problem number 3, I'll just multiply this out, right? So I'm gonna get 1. Well, I don't need to. This will be cosine of and then minus e to the minus t cosine of 3t plus 4 e to the minus 5t cosine of 3t. Okay. All right. So what is this going to become? Well, this one here, right? This, when I take the Laplace transform of this is going to be s over s squared plus 9, right? That's what this is. This one here is going to be minus, but now I have to put in the s is shifted, right? I did this intentionally so you can kind of maybe start to see a pattern. I actually did these problems yesterday. Okay, so, right, so, yeah, I did this intentionally so you could see, okay, here, when you just have the cosine of 3t, you got s and then s squared plus 9. Now this is being multiplied by the minus t, so we got the, so now we have to put in, we have to shift the s minus 1, right? Okay, and then this one here would be just 4, and now this is a plus, right? Excuse me, this is a minus. Oh, this is a plus. Did I make that? Okay, I made that. It's different in my notes. Yeah, so this is right. This is if I make this a minus, then this, yeah. If I make this a minus, then this is a plus, right? And then this here would be, I actually copied the problem wrong. Okay, in my notes, I got this as a plus. Okay, but that's okay. So this is going to be a plus here now, right? Because I got the minus here. Now this is going to be s, it's going to be plus 5, right? And then it's going to be s plus 5. And then this is going to be 9. Okay. Right? Okay, so that's so this is the Laplace transform of this thing. Okay. All right.
Professor, would you also add a 4 at the end of that? Because that would be what f at 0 would be.
I'm not sure I understand your question.
So the Laplace transform of f of x includes a point of f at 0, correct?
You mentioned something about the 4. What was your question about the 4?
Would there be an integer value of 4 because of f of 0 would be?
No, I got this 4 here. So this 4, you know, if I was just looking at the Laplace transform of this, I could take the 4 out, right? I don't understand your question. Maybe you could rephrase it again. Hello?
Yeah, I'm not sure how to rephrase it more clearly.
Well, say it the way you should have said it before.
So you're taking the Laplace transform of some function, right? The function wouldn't then the Laplace transform of that is s f of s plus f of 0, correct?
Plus f of 0. Do you understand going from here to here?
Yes.
Okay, so what, and you understand going from here to here?
Yeah.
Okay, I think maybe you're talking about the inverse transform, which we haven't done yet.
I might.
Well, let me continue, and then, you know, if you're still confused about something, we can talk about it after class. Okay. All right, so I want to do this one now. Now, this one here is a little, right, we have the unit step function here, okay? And remember now, the other theorem that we have to use for the unit step function is e to the at, right? And this is f of s minus a, okay? All right, so so first of all, okay, so this is, okay, so I want to take the Laplace transform of this. But this is not the, oh, this is the unit step function. That's not the right formula. Let me find the formula for the unit step function. Okay, so yeah, this is the formula here for when we want to, when we're doing transactional, right? So the other formula that you need to know is that if we have the Laplace transform of some function, right, times the unit step function, right, that this is equal to the function this is equal to e to the as, right, minus, right, and then it's times the Laplace transform of f of t plus a, right? This is one of the ones that we derived yesterday, all right? That when we have the unit step function, the Laplace times a function, right? We got the unit step function times a function, okay? It's we have to, the Laplace transform is e to the minus SAS, and then the Laplace transform of the function plus a, all right? So we gotta do that, okay? So let's see how we do this. So first of all, I can write this now. I could just use this formula here, right? I can just use this formula here. So I'm going to get e to the minus pi over 3s, right? Because I got the minus pi over 3 here. So I have e to the minus pi over 3s. Then I got the Laplace transform of sine of t plus pi over 3, all right? Now, how do I figure out the Laplace transform of sine plus pi over 3? In previous examples that we did, we had like the sine of t plus 2 pi, right? That's just equal to the Laplace transform of the sine of t, right? And I think there was another case where we had the cosine of t, and then we had a minus pi. Then we had a pi, so that's the same as minus the cosine. But here now, how do I figure out the Laplace transform of sine of t plus pi over 3? Okay, well, I have to use the trig identity that the sine of a plus b is equal to the sine of a times the cosine of b plus, let's see, plus the cosine of a sine of b, right? I have to use that trig identity. Now, when I use that trig identity, what's going to happen here? I'm going to get the sine of t, I'm using the trig identity. Well, let me write it out. You get the sine, of t plus pi over 3 is equal to the sine of t times the cosine of pi over 3, right? Plus, this would be the cosine of t times the sine of pi over 3. Okay, a little sloppy there. All right, so this is telling me now that the sine of t plus pi over 3 is equal to, now what's the cosine of pi over 3? That's 1/2, right? It's cosine function. Yeah, that's 1/2. So I got now 1/2 the sine of t plus, okay, the sine of 1/3 is pi over 3. It's square root of 3 over 2, right? Right, this is the square root of 3 over 2. And okay, so now I got, so what I have here, so I need to take the Laplace transform of this thing, okay? And so my answer then is going to be e to the minus pi over 3s, and then the Laplace transform is going to be 1/2. Then the Laplace transform of this, right? This is just going to be 1 over sine squared plus 1, right? Plus the square root of 3 over 2, and then this is the cosine. So this is going to be s over s squared plus 1. All right. So I want you to see a problem that when you get something like this, you have to use the trig identities. If this was cosine, or if this was a minus sign here, you have to break it up this way. All right. Now, I think the problems, even the problems on the exam, if you have something, I think it turns out that it's s plus pi or s, which you don't have to use the trig identity. Okay. All right. So that's you just need to be aware of this. Any questions? Okay.
I know where I was confused on problem 3. I was taking the Laplace transform of f prime with the Laplace transform of f.
I'm having trouble understanding. Did you repeat your question?
I was just saying that I know where I was going wrong with problem 3. I was mistaking the Laplace transform of f prime.
Oh, okay. Oh, okay. Yeah, right. We're not, yeah. Right. Okay. All right. Any questions on this problem? I think this is an interesting problem. Okay. All right. So now we're going to do some inverse, but I want you to try to do them first. Let me see. I made some up here. That's what I was doing this morning. Okay. So let's see. So now we want to do the inverse Laplace transform. And I did put these in my notes. Inverse Laplace transform of that one. That one. And let's see. Okay, try these 4. By the way, I did add this to my notes that sometimes it's easier to use this. As far as the inverse. Right. Where now in this case here, n goes from 1 to 2 to 3, dot, dot, dot. We also have this. And in this case, n goes from 0 to 1 to 2. Okay. Many times in a problem, you're going to see an s raised to the nth power. And I always find it easier to use this form, but you can also use this form. But then you have to figure out, okay, if you don't have an n factorial here, you got to put something down there. So you can also use this. Right, these are both equivalent. So I would, in this problem here, I'd rather use this. Made it too easy. I made this one a little bit too easy. Why don't you try this? I also want you to try that. Give you a couple more minutes. Okay, let me go ahead and solve these. Let's see. Well, the first one, right? If I just take a look at the 1 over s, right? I got the s squared here. So this is just going to be t, right? This is going to be t. But then I got the +4, right? So I hope everybody sees that this one here is a simple one. Hopefully you think it's simple. This one here is just going to be e to the minus 4t times t. Okay. All right. So this one here, I actually wanted to make this a little bit harder, but let me wanted to start out with something differently. Okay. This here is going to be sine, right? So this here, I hope everybody sees, this is going to be e to the 2t. Right, here's the minus sign. So now it's a plus here. So it's e to the 2t, and then this is the sine of t. Okay. Now, I actually wanted to start you out with this. So let me do this one here. It's actually going to be, it's going to come out to be this, but I wanted to give you this. Make sure I copy it right. This is really what I wanted to start you out with. And what I want you to understand is that when you see like an s squared and a minus s and 5, you want to complete the square. Okay, you want to complete the square. So remember, when we complete the square, I divide this by 2, right? it doesn't matter if this is a minus sign, divide it by 2 and then square it. So I'm gonna write this as s squared minus 4s, right? Plus 4, right? Plus 5 minus 4, right? I added a 4, so I got a minus 4. Now here I have a perfect square, right? Here I got a perfect square. So this is going to be s minus 2 squared, and then this is going to be plus 1, right? So this is what I really wanted to start you out with. I wanted to give you this. So then this becomes 1, right? So now this becomes what we have up here. So now I got the inverse Laplace transform of s squared 2 minus s squared squared plus 1, right? Which is what we have here. So I wanted you to start out with this and realize you have to complete the square to get this, and then you get this. Okay. Now the next one. Okay. So now what is the if I know that let's see, let me do this. Right. The difference between this and this is that here I got this e to the minus pi over 3 times s, right? So the Laplace transform of this thing, right? Every place I have a t, I have to shift it by minus pi over 3, right? Every place I have a t, I have to shift it by minus pi over 3, and then I have to multiply by the unit step function. So the Laplace transform of this thing, right, is going to be e to the 2, and then it's going to be t minus pi over 3, and then it's going to be the sine of t minus pi over 3 times the unit step function. Okay, so I want everybody to make sure they understand the difference between this one and this one. And this one here, you know, we're using the what we determined yesterday about the when we have the unit step function, right? When we take the inverse Laplace transform. Okay, so don't forget, everybody seems to forget to multiply by the every place you have a t. You know, if this was even more complicated, you know, maybe you had another t here, then you know, you make sure you have to shift that t. So every place you have to have a t, you have to shift it, and then you got to multiply by the unit step function. Okay. Now the last problem. Let's see. I guess I can do it here. Let's see. I can start it here. The last problem. Once again, the first thing, like I said, when you have when you got something like this, the first thing you want to do is complete the square, right? So let's see. So here too, I can complete the square. I'm going to write this as just looking at the bottom here. This is going to be s, and then I'm going to add 4, right? Plus 13, right? Minus 4, right? So now this is a perfect square, right? So this is going to be s. This is going to be s plus 2 squared, and then this is going to be 9. Okay, so let's see. So what do I have now? So now I got the Laplace transform. I got the 2s plus 3, and now I have this s plus. Okay. All right, that's what I have now. All right. Now, okay. I have this s plus 2 here, right? So it would be nice if I had an s plus 2 on top. I don't have an s plus 2 on top, right? Let's see. So what's the best way to do this? Okay, I can break. I'm going to break it down like this. There's more than one way of doing this. I'm going to write this as 2s plus 2, right, plus 1. Okay, and now I have let's see. So now I have s plus 2 squared plus 9. And over here, I got s plus 2 squared plus 9. Okay? All right, now what? Let me take a nice look over here. Okay. Let's see. All right. I probably should have wrote that as 3. If I take a 2 out of here, let's see. But that still gives me a 2 here. Something's not right. If I take a 2 out of here. I want to get a s plus 2. Let's see. This isn't right. I think the best way to do it. How the heck? This is 3. I added the 3 here. I'm looking at my notes. I think my notes are wrong. Okay, so anyway, so let's see. So if I make this a 4, I can make this a 4. Did I copy it wrong? If I make this a 4, and then I minus a 3. Right, make this 4 minus this a 3. And then this is going to be, so now I can factor the 2 out of here. Right? My notes are wrong. That's what's confusing me. So now, okay, so now it's okay. Right? So okay, so I have this, right? If I make this a 4, right? Make this a 4. And then this would be a minus, yeah. Well, let me start from this point here. We're finding the inverse Laplace transform of 2s, is right, I have 2s plus 3 over, and now I have s plus 2 squared plus 9, all right? All right. I want, okay, so my notes is wrong, damn it. Okay, sorry. All right, so I really want this to be, if this is a 4, right? I can make that a 4 and then minus a 1, right? Okay, then what I could do is, then here now, I could factor out this 2. Now I get s plus 2. There's no square here. S plus 2. S plus 2 squared plus 9. And then I got minus 1 over s plus 2 squared plus 9, right? Okay. So, okay, so now this is 2. Now this is e to the minus 2t, right? And then this is going to give me the, yeah, then this is gonna give me this, oh, this is just a 9 here. Okay, so this is a 9 here, so this is gonna be a 9, this is a 9, that's right. Yeah, so the sign, yeah, this is correct. I got it mixed up. So this is now the cosine. This is gonna be the cosine of 3t, the cosine of 3t, and then minus. This will be. I got to put. I need a 3 up here, so I got to put another 3 here and another 3 here. So this is gonna be 1/3. 1/3 the sine of 3t, and then this is also multiplied by e to the minus 3t. All right, so my answer is correct, but my work is wrong. See, but I would get it right on the test because I realized that it wasn't right. So let me go through this. Okay. So so we're good up to here, right? We're good up to here, right? I really want an s plus 2 here, right? I want an s plus 2. So I make this a 4 and minus 1. I didn't do that in my notes. I make this a 4 minus 1. Okay. Then I can factor out this 2, right? So now I got the s plus 2 and the s plus 2 here. So this is going to give me the cosine, right? This is going to give me the cosine of 3t, right? Because I got the 9 here, right? Remember the cosine. Cosine is s over s plus s squared plus s plus k squared, right? This is what cosine is, right? So okay, so everybody's with me up to here, right? I factored, I added a 1 and then subtracted 1, so I get this, right? Then I pull the 2 out. Okay. And
Excuse me, Professor.
I need a 3 up here. Just let me finish this. I need a 3 up here, right? Because of the sign has a k here, right? So I need it's a k down here. It has a k squared, so I need a 3 up here. So so this is going to give me a 1/3 here, right? Okay, so the final answer is 2. Just let me finish this up. 2 e to the minus 2t cosine of 3t minus e to the minus 2t divided by 3 sine 3t. I was looking at my notes, and my notes got the right answer, but it doesn't look like it's right in the middle. Okay, someone had a question?
Can you please explain why you added 1 then subtracted 1?
Yeah, the reason why I added 1 and subtracted 1 is that I want to get an s plus 2 here,
Right.
right? So if I add 1 and subtract 1, I'm going to get this s plus 2. Then I could factor this out. I could factor a 2 out of here, right? I could factor a 2 out of here, and I get the s plus 2.
Right.
So that was the whole thing. I needed to get this s plus 2. The answer is right in my notes, but it doesn't seem to me like the work is correct. Okay, but I guess this was a WebAssign problem, and I got the final answer correct. Any other questions? Sorry that it took me so long to. Sometimes I'm better off not looking at my notes.
Professor?
Yes.
Okay, so I understand now why you added one, it's so you could cancel out the, or you could get them in the same factors. And
Right.
then,
You see here, I got this s+2 here squared. And here, it would be nice if I have an s+2 because then this is gonna be the cosine.
right,
And it's
Oh,
gonna be
okay.
shifted by this. See, sometimes these problems are, like I said, the inverse is a little bit difficult, is that you sometimes have to look ahead and know what you're trying to get and know you know, well, first of all, you have to know that the cosine, right, is given by this, right? The inverse cosine is given by this. And then when I have a shift, you know, I need to have a shift. I want this s and this s to be the same.
right, and that's where the e to the negative 2t comes from.
Right, right. And so
Okay.
the trick is, like I said, these could be a little bit tricky. They're not hard. So the trick is, you know, is getting this and this the same. Okay, I don't think I gave you anything like this on the exam. I did give you one where you have to complete the square, though. I'm pretty sure you have to complete the square. Okay. All right, what I want to do now is I want to solve a problem with using the Dirac, Dirac. Let's see. Well, let me do this for a second. Let me go to share screen. What time we got? Spent a lot of time on that. I should say I spent a lot of time on that.
Professor?
Yes.
So, this is another method to solving something that's oh, I'm sorry. I don't know how to phrase this question. Because
Well, plus
with-
you need to use, if you have piecewise continuous functions, it's another method for solving differential equations, right?
right. I was actually gonna ask, could he, if there wasn't any shift, would you still have to only use fractional decomposition to solve for the Laplace?
It turns out there is another way called convolution, and I did post it in I did post it on Blackboard. Let's see, pretty sure I posted it. Yeah, notes on convolution. There is another way of doing it, but
Okay.
sometimes it's more complicated. You have to do integrals, and sometimes it's easier. But we're not required to go into convolution.
Okay.
But if you go into electrical engineering, you're going to learn about convolution.
Gotcha.
Okay, so let me just share my screen for a second here. Like I said, we're not doing anything new today. Okay, hope everybody sees the screen. So I added a section. Now I added this section here. Laplace transform example problems and solutions. So we just did some of the problems, like for example, jumps. I guess I got a lot of things open. Like we just did this problem. Okay, so these are like, you know, we did this problem here. You know, we did this problem, and this is the problem where, you know, this is the right answer, but the work is wrong. Yeah, this work is not right. Doesn't make sense to me. but the answer's right. But we got the right answer. Okay. What I want to do now is I want to solve it. It turns out these problems are not long. So you see, you got other problems here that I put down to find the inverse Laplace transform, where you have to do partial fraction decomposition. I put in an electric circuit problem. So here's the problem. Let's see, where's the problem I want to do? Okay, here's the problem I want to do. Guess it's not. My computer, it doesn't move and then suddenly it jumps. I guess I got too many windows open. Right here. Give me a second here. It's not my best day. Okay. All right, here's the problem I want to solve. Okay. So I'm going to do it on, but first, let's just take a look at the problem, and then we'll, I'm going to write it out on paper. But the problem is that we have a spring mass system, right? We have a spring mass system, and we're told that at time t times t equals pi, the mass is struck by a force of 4 pounds, okay, for a very short period of time. And the idea is that the striking of the mass can be modeled using the Dirac delta function, all right? And we want to find x, we want to find the position as a function of time, where we're told that the dampening force is numerically equal to the velocity, right? We're also told what the mass is, right? So we're told that the mass is equal to 0.25, and that the spring constant is equal to 2 pounds. So I'm making sure I get everything. And it's at time t equals 0, it's at rest, right? And it's not moving, right? But then at time t equals pi is when we hit it with a force of 4 pounds. Okay, so all right, so let me solve this problem now that we understand. Let me solve this problem. It shouldn't take long to solve this problem. I want to go back to my paper. Okay, I just wrote down the information, so now I want to solve this problem. So let's see what happened. Okay, so let's see how much. Yeah, I could finish it up. Okay, so first of all, remember the equation for a spring mass system is given by m double dot. Is everybody seeing what you're able to see what I'm writing, right? Okay, that's my differential equation. And we're told that the mass, right, is a quarter of a slug. So I'll write that as 1/4. My beta is 1, right? Beta is 1. We're told that the dampening is numerically equal to the instantaneous velocity. So that means beta is equal to 1. And we're told that the spring constant was 2. And that we're striking this with a force of 4 pounds. So this is our force, right? Right. So you are going to get a problem like this. That's all I want to go over. All right. So remember the The force then is actually given by 4 times the Dirac delta function, right? So we're hitting this with a hammer or something. We're striking it. And that's what the Dirac delta function allows us to do. If you have a spike in a circuit, a voltage spike in a circuit, you know, you would model that using the Dirac delta function. Okay, so my differential equation now becomes 1/4 x double dot plus x dot, right? Plus 2x is equal to 4, right? So I can write this as x double dot plus 4x plus 8x is equal to 16. Oh, and okay. All right. So so now we take the so these problems are actually pretty short. If I take the Laplace transform of both sides, right? Now remember, now we're starting from the initial position is 0 and the initial velocity is 0. So this x double dot, right? This x double dot, when I take the Laplace transform of it, that's just going to be s squared, you know, big X of s, right? Because the other terms are 0, right? And then I'm going to have 4. Right now this here, right? The Laplace transform of this is just s, right? Times big S. I think I got to include the 4, right? I got this 4 here, so it's 4 times big S, right? Times S. I got to put the S in. S, right? I'm using the properties that we learned about the first derivative and the second derivative, right? The second derivative has the s squared, right? And then the initial conditions, right? And the first derivative just has the s, right? And then I got plus 8. And then this is equal to now, remember now, the Laplace transform of this thing is just going to be 16, right? Times e to the minus pi over pi times s, right? That's the, you know, it's in the notes. This is the Laplace transform for the Dirac delta function. We did that yesterday. All right. So now I have to solve this. I have to solve this for s, for big, right? So let's see. All right. So this is going to become, factor this out. So I'm going to s squared plus 4s plus 8, right? Let's see. And that's going to be equal to, okay. All right, so this one turns out to be pretty straightforward. Okay. So what I'm going to do here now, remember, I said that when you see something like this, you're going to complete the square, right? So I can complete the square on this. If I complete the square, let's see, I can write this. Let's see, this would be 4. Well, let me do it over here. I take half of this and square it. So this is going to give me s squared plus 4s plus 4, right? And then plus 8 and then minus 4, right? I added a 4, I got a minus 4. So this is now a perfect square. So this is just going to be s squared plus, not a squared, it's a perfect square. Right? So this is going to be s plus 2 squared, and then this is plus 4, right? So that's what I have down here now. This is s plus 2 squared plus 4. Okay. All right.
Excuse me, Professor.
Yes.
Before we continue, can I just make sure that I'm understanding the steps that you're doing to complete the square. So you're
Okay.
the 4s, you're just taking half that and you're squaring it. That's how you got the s squared plus 4s plus 4 term, right?
Right.
But because you added the plus 4 term inside the parentheses, that's why you're also subtracting -4, right?
Exactly right. I can't just add a 4. So the
Right.
fact when I add a 4 and subtract a 4, that's the same as adding 0, which is fine. Right, so
Okay.
that's how you complete the square. You complete the square by, you take your half of this term here, right? And then you square it.
Right.
And it doesn't matter whether it's a minus or plus here.
Okay.
Okay, all right, so we have this now. All right, so notice I can write this like this. See, if I have a 2 here, right? I want to have a 2 here, right? Because if I have a 2 here, then this is going to give me sine, right? Because remember, the inverse Laplace transform of sine is right. So I got a 4 here, right? I got this 4 here. If I have a 2 here, right? You know, this is sine, right? This is sine. So if I have a 2 here, I'm good. That this whole thing is going to give me sine. All right. Okay. So so let's see. So I can write this now. I can write this as 8. I'm going to write it as 8, and then I'm going to write this as 2 e to the minus pi s, and then I'm going to write this as s plus 2 squared plus 4. Okay. So now this whole thing here is this is cosine, right? That's cosine. It's sine. I'm trying to rush. It's sine, right? And it shifted. It shifted by 2, right? It's shifted by 2. It's sine, and it's shifted by 2. So okay, right? It's sine, so it's shifted by 2. But now I also have this e to the minus pi s, right? So let's just, right? We did this before. Let's just forget about this, right? I can write this as let's see, right? As 8 e to the minus times the sine of t. Now that's if I didn't have the e to the minus pi s, but I got the e to the minus pi s, right? So I got to shift. I got every place I have a t, I got to shift it by minus pi, right? So, you know, once again, this is if I exclude this. So my final answer now, say x of t is going to be 8 e to the minus 2, and then this is going to be t minus pi. Yeah, t minus pi. T minus pi. To t minus pi times the sine of t minus pi, and then times the unit step function, which is t minus pi. Okay, let's see. All right, is everybody with me up there? So that's my answer. And okay, so that's the answer. Any questions? So let's see. So in my notes,
Professor,
yes.
shouldn't the t minus pi inside of the sine be multiplied by 2?
Oh yeah, forgot the 2. Yeah. Yeah, it should be p minus 5. I'm rushing a lot today. It should be written like this. you looking at my notes or you just realized? Yeah,
No, I just realized that as I was
very
writing
good,
it down.
very good. Okay. Yeah, let me just, go back to here. Okay, so you should be seeing the screen again. And so here's the answer. Okay, this is what's in my notes. And you know, we can also find the minimum value. But what I want you to notice, I didn't want to draw it, but here's a graph of what it looks like. And it should make sense to you, right? Nothing's happening, right? Nothing's happening. And then we hit it, right? We give it an impulse, and then the thing starts doing something, okay? And it's actually vibrating, but it's vibrating very little. You can see the Desmos did give you the places where it crosses the axis. So it's going up and down here. It's very small. It's because the dampening is large. If I gave you a problem with a smaller dampening, you're going to see this go up and down. I think that's, so you will have a problem like this on the exam. Okay, like I said, you're going to have let me just talk a little bit more about the next exam. You're going to have 3 problems where you have to, problem number 1 would be 3 problems where you have to find the Laplace transform, kind of like what we did today. And, you know, it won't be as hard as the last one we did. And then you'll have 3 problems, not that it was hard. It was confusing me because my notes were wrong. And then you'll have 3 problems where you have to find the inverse Laplace transform. So that's problem number 2. So problem number 2 has 3 things that you need to find the inverse Laplace transform. And then you're going to have to solve a differential equation, second order differential equation, where you have the unit step function, right? And then you're going to have to solve a differential equation where, it's an application where you have the Dirac delta function. And it is going to be a problem like this. Okay, so
Professor,
yes.
before we move on, can you go over the significance of factoring out the 8 of this problem?
Factoring out the 8. Could you tell me what?
So
okay. You mean this here?
Wait, sorry. Are you pointing on the? Oh yeah. Here.
Yeah,
Why?
okay.
I don't understand the significance behind factoring out the 8, and then
Okay.
and then I remember you circling the form of 2, and then the bottom part.
Yeah. Okay. The reason why I took the 8 out of the 16 is to show you that when I put the 2 here, right?
Right.
I got a 4 here, right? Now remember, you need to know the Laplace transform of sine, right? The Laplace transform of sine is k divided by s squared plus k squared.
Ah, I see. So you factored out the into that form. I see.
Okay.
All right, that makes perfect sense.
Okay. And so, yeah, I mean, sometimes when I do, after a while, when you get experience in doing this, I could sometimes just write this out, okay? But I try to show the different steps, especially when you're learning. Okay. So in this problem here, I don't think let's see, you can also find the max and min, right? So this thing's gonna jump. Everybody should know how to do this from calculus 2, or from calculus 1, actually. Right, you just take the derivative and set it equal to 0, and then solve for the time. Right, you take the derivative, set it equal to 0, and solve for the time. then you get T, right? Take the, so that's what's going on here. I think I do actually define the min and max values. So make sure you can follow this. I don't think you have the time to go through it all. There's other things I want to talk about. But it's pretty straightforward, right? Does anyone have a question? So you take the derivative, set it equal to 0, you solve for T, and then once you get the T value, you plug it into the equation, and here you get a max value, and here you get the min value. Okay. And you see too that if you were to graph it, you would take the solution and graph it. That was shown. So here's the max. Here's actually calculating the max value and min value. But Desmos, or even the hand calculators, will give you, Desmos actually will give us the value, right? Like Desmos gave me the max. If I put my cursor, if I graph this, I graph the curve, and I put it, and you put the cursor at the top point here, it'll tell you what the X and Y coordinates are. Now, in this case, we're using X and Y, but this is T. This would be T and X, right? So the max value, it turns out to be at a time of, that's interesting that the max value does not turn out to be, well, it turns out to be a little bit after, right? We hit this thing at, we're going to hit this thing at pi, right? We hit this thing at pi, and it reaches its max value, not instantaneously, but it hits its max value at 1/8 more. Yeah, that's kind of cool. And that's its max, and that's the min, and that's what we get to when we calculate. Okay. So I did want to show you that I have additional problems here. And somehow this is not making sense to me. From here to here doesn't make sense, but this is right. The answer, bottom answer is right. Okay. I also wanted to show you it's not required for this course, but there's what's called convolution. It's kind of cool. If you continue in electrical engineering or signal processing, you'll definitely learn about convolution. But it turns out that if you have two functions, all right, and this is the definition of convolution, that instead of breaking it up into partial fractions, if you take the convolution of the two functions, I have to define, and this is the definition of convolution, but if you take the convolution of the two functions and you break them up, then that gives you the Laplace transform, okay? And then the inverse transform, if I have two functions that look like this, that's just a convolution. So an example better explains it, that that here, if I have something like this, right? I can write f of s, right? I can break this up into, I'm showing here, I can break it up into partial fractions, and this is the answer you get, right? You break this up into partial fractions, you get this answer, okay? If I use the convolution method, I can write this as s minus 1, and this is, and 1 is s squared. So this is 1, and this is the other, right? And then, let's see. And then I have to know, okay, so this turns out to be ET, and this turns out to be T, right? And then I do the convolution of those two. And you see, I get the same result. So you can take a look at this. It's not required for this course. It turns out that sometimes these integrals can be pretty complicated. In this case here, I actually picked a case where, the integral, you still have to integrate this by parts, or you can just use a table of integrals. Okay, where are we? Okay, this is actually what convolution is really about. It's an overlap of two functions. Okay, let me see if there's anything else I wanted to point out. Okay. Yeah, probably if you check Blackboard Saturday evening, I should have the exams all graded. Okay, hopefully everybody handed in the exams. So I should have more graded by Saturday evening. Let's see what else. Okay, so any questions? So Tuesday we'll have the next exam. I think I'm finished with the Laplace transforms. And so what I'm going to be going over next is I don't know if you see my screen. Just so what I'm going to be going over next, let's see. And this is our last topic. We're going to look at, do you see my screen? Did someone tell me you see my screen, right? System differential equation? Okay, all right. So this is going to be the next topic. And, you know, I have to talk about eigenvalue equations and finding the eigenvalues and eigenvectors. And this is the way you have to solve it on the exam. All right. So, and it turns out just like there's going to be different cases where the eigenvalues could be real, they could be repeated, or they could be complex. That should probably sound familiar when we did systems of linear equations, right? But we're only going to deal with the case where the eigenvalues are real and distinct. Okay. So we'll be solving a system of linear equations that looks like this, and it's pretty straightforward. Once you learn about how to find the eigenvalues and eigenvectors, you really have solved the problem. Let's see, I just want to see something here. So for example, on the next exam, which you can have on Tuesday, you can have a problem just like this. So if you want to look ahead, it's going to be just like this with different numbers. All right, we have to find these. And once again, we're going to go over this on Monday. And it's not that big. I find that most students have problems with the Laplace transforms. I think that's especially trying to find the inverse Laplace transform. But the problems you're getting are pretty straightforward. All right. All right, that's all I have for today. I'd like to leave a few minutes for additional questions, but I'll see you all on Monday. Have a good weekend. And there's a lot of homework due this weekend. Okay, there's a lot of homework due this weekend. And the thing is, I kept on pushing the early assignments to the right. Okay. So I hope you didn't wait to this weekend to do all the WebAssign homework. Okay. All right. So have a good day.
You too, Senpai.
Thanks, Professor.
Okay. Have a good day.
Have a good day.
Hello? Someone have a question?
No, I was